Hello everyone, this is Dr. Young, and in this video we're going to continue talking about stoichiometry, and we're going to specifically go over this idea of percent composition by mole or by mass, where mass is hands down the most common one. This is related to the idea of mole ratios, even though we won't be using them as conversion factors in this video. We'll be using those exclusively in the following videos, but I wanted to take a few minutes to do a couple practice problems with you to make sure that we understand how to solve any problem that involves percent composition. So just to quickly remind you, right, when we're talking about mole ratios, or when we look at a formula, right, the formulas give you the ratios of elements in a compound, right? So in a previous video, I was talking about acetone here, where I said if you look at this, I know what the ratio is between carbon, hydrogen, and oxygen because it's given in the formula, right? I know that for every 3 carbons, there are 6 hydrogens and 1 oxygen. Right, because that's simply given by these subscripts, and I know there's not a 1 written here, but really you want to think about there being a 1 behind the O, but they're just given there, right? So that's the ratio of, if you're looking at an individual molecule, that's the ratio of atoms, or if you're looking at about that material in general, that's the ratio of moles, right? That there's, for every 3 moles of carbon, there's going to be 6 moles of hydrogens and 1 mole of oxygens. Now, percent composition is just talking about what percentage what percentage of that compound are these different elements. And you'll see 2 different percentages. Occasionally people talk about percent by mole, but this is relatively rare. We don't really care about the percent by mole as much. We care a lot about the percent by mass, though, because that's one of the ways that we help discover the compositions of new things. So you're going to see a lot of percent composition by mass problems more often than percent by mole. This is definitely more common. Now you're going to see 2 different types of problems with this percent by mass stuff. One of them is going to be trying to determine the percentage in grams of different elements in a formula. So that's the first type. Whoops. That's the first type here. And then the second one will be using percentages to determine the formula of some unknown compound. That's the second type. And I've written down some steps to help you figure out how to approach these problems. So for the first one, the percent of an element from the formula, you're just going to take that formula, and then you know the mole ratios because you got a formula. So you're going to convert those moles into grams. And once you have them in grams, you just use the periodic table to figure out. Then you just have the grams and you figure out what percentage there are, right? Part divided by the whole. Now, if you are trying to find the formula and you have percentages, what you do is you just pretend like you have 100 grams of that stuff, and then therefore you know how many grams of each individual element you have in that compound. And I'll show you what I mean in a second. But then once you know how many, you convert those grams into moles, and then you figure out the ratio of the moles there to get your formula. Because again, formulas are a type of mole ratio. So let me show you, let me give you some very specific examples of how to do these problems. But to first highlight the differences, right, between percent composition by mole versus percent composition by mass. If you're talking about moles, right, if you look at C4 or CH4, which is just methane, you only have 1 carbon for every 4 hydrogens, which gives us 5 atoms altogether. Right, so if you're doing percent by mole for carbon, it's 1 of those 5 total atoms, or in other words, it's only 20%, right? By a mole or by a molecule, it's only 20% of the composition of a methane. If you look at the hydrogens, they make up 4 out of the 5 of those total particles, right? Individual atoms, or if you're looking at moles, and that means that they make up 80% of the total number of atoms, or the total number of moles of atoms in methane, if you have a mole of methane. Now that's very different. I'll show you how to come up with these numbers, but that's very different if you look at the mass, right? We're talking about grams. If you look at the mass, that looks like an 8 grams. If you look at carbon in terms of mass, because remember that carbon weighs about 12 grams per mole, whereas hydrogen only weighs 1 gram per mole. Carbon actually makes up 74.9% of all of the mass of methane, whereas hydrogen only makes up about 25. Right, so hydrogen makes up 25.1% of the mass of the molecule, right? And it kind of reminds me, and so these are opposites, right? So in the percent composition by mole, hydrogen makes up most of it. But if you look at by mass, carbon makes up most of it. And so that kind of reminds me of that like joke / riddle thing where someone asks you which weighs more, a ton of bricks or a ton of feathers. And if you interpret ton as meaning like a lot of, like which weighs more, a lot of bricks or a lot of feathers, then, well, of course, bricks weigh more because, a brick weighs a lot more. So if you have a ton of bricks versus a ton of feathers, bricks weigh more. But if you think about ton as being the actual like 2,000 pounds, then 2,000 pounds of bricks weighs the same amount as 2,000 pounds of feathers, right? They both weigh 2,000 pounds, so there is no difference. Neither one weighs more. Similar idea. Are you talking about counting the number of individual pieces, like you are with a mole? Or are you talking about the actual mass? If you're talking about the masses of things, in which case you're talking about the grams. It can be very, very different. And again, we're looking at percent composition by mass much, much more often. So let's look at a practice problem involving that. Right? Percent of an element from the formula. So here's a question. What percent composition of hydrogen is in aspirin? I need a verb in there. Is in aspirin, right? And aspirin's C9H8O4. And so the first thing we do is we convert those moles into grams, right? So step 1, convert moles into grams. And these moles just come from the formula, right? Because I've got hydrogen, I've got carbon, and I've got oxygen here in my formula. So I'm going to do the carbon first. So if I look at carbon here, it looks like I've got 9 moles of carbon in 1 mole of aspirin. And if I look at the periodic table, I know how to convert that into grams because on the periodic table it says that carbon weighs 12.011 grams for every 1 mole of carbon. And if I do that math, I see that that ends up being 108. Oh, whoops. Sorry, I switched that up. See, this is why you gotta make sure that your units cancel. My units don't cancel here, right? I have moles up top and then grams on the bottom. That doesn't work. Those don't cancel. I'd end up having, if I did this problem, I'd end up having mole squared on top and grams on the bottom. So I need to fix that. So that my moles cancel, right? 1 mole of carbon weighs 12.011 grams of carbon. So I can get grams of carbon. If you multiply those out, you're going to get 108.099 grams. And then I do the same thing with the hydrogen, right? I've got 8 moles of hydrogen because there's a subscript of 8. I look at the periodic table, I see that 1 mole of hydrogen weighs 1.0079. If I multiply those out, I get 8.0632. And then lastly, if I do oxygen, I've got 4 moles of oxygen. Look at the periodic table. I see that 1 mole of oxygen weighs 15.999 grams. And if I multiply that out, I should get 63.996. Now, what we kind of want to remember, right? So then step 2 is to convert that gram into a percentage. In this case, I'm asking about hydrogen. So I want to know if these are the masses of carbon, the mass of hydrogen, mass of oxygen, what percentage is 8.0632 grams of hydrogen? What percent is that? And so you're just going to convert, I'll just say here, find the percentage of a given mass. And so remember that your percentages, right, to find a percent of something, you just take the part, the thing that you're looking for, over the total, or over the whole, and you multiply it by 100. So I know the part here, right? I know the part. The part for me is the 8.0632 grams of hydrogen. And I need to know now the total, which is all this stuff added up. So all I need to do is just add up all of these things, right? My 108.099 plus my 8 plus my 63. That all is going to add up to 180.158 grams total, right? So I just added those all up. So that's my denominator. That's what all three of those added up equals. So now I can figure out what percentage, so total, what percentage of that total is just hydrogen, and then I multiply it by 100. And what we find is that the percentage equals about 4.5%. And that would be my answer. Apparently, in this compound, by mass, hydrogen only makes up 4.5% of the total mass of aspirin, of the total mass, right? The other 95.5 must come from the carbon and from the oxygen. And if you look at these numbers, obviously most of it comes from carbon. And so this question could have asked, what's the percent composition of carbon in this? If I was asking about carbon, all I would do is I'd just change the numerator. I'd just change this numerator to the 108. I'd say 108.099 right here. And then I'd find that percentage. So I could find the percent of carbon. I could find the percent of oxygen. I just need to change the numerator, the thing it is that you're looking for. So that's how we set up these questions. So using this setup here, I want you to try one yourself. So let's take a look at this. Same exact type of question. What is the percent composition of calcium in limestone? And I give you the formula of limestone. It's CaCO3. So I want you to pause, see if you can do this exact same thing. Remember that the first step is to convert those moles into grams. And then once you have those grams, you're going to find the percentage of those grams of the total. So go ahead and pause, and then we'll go over this one together real quick. So again, hopefully you gave yourself some time to practice this here. So we're going to do the exact same thing. We've got calcium. Apparently there's only one calcium in here. So 1 mole of Ca. Using the periodic table, 1 mole of Ca is 40.0, what is it? 078. That's pretty easy math. Apparently 1 mole is exactly that of calcium. Next I have carbon. So it looks like there's only 1 mole of carbon also. Again, easy math for us. 12.011. Sorry, that's my phone. So 12.011 grams of carbon. And then lastly, oxygen. Looks like there's 3 moles of oxygen for every 1 mole of limestone. So I know that every 1 mole of oxygen weighs 15.999 grams of oxygen. And if I multiply those together, I get 47.997. And so again, right, it's the same thing. A percentage equals part over the whole times 100. In this case, the thing that I'm looking for is calcium. So now in this case, my part, right, if I'm finding the percentage, my part is going to be the 40.078 grams. But I need to figure out what the total is here. So the total of this, again, I'm just going to add these all up here. The 40 plus 12 plus 47, and change is going to be 100.086. This happens to be right near 100, so that makes the percentages mentally easier, but still, same process. So 100.086 grams times 100. And, we should see that it's around 40. And if we do this, sure enough, calcium apparently is about 40% of the mass of calcium carbonate of limestone. So here's just another example, right? And you could do this with any, if you know any formula of any substance, you can ask yourself what the percent composition is of any of those components. So again, instead of calcium, I could have asked you about oxygen, and the only difference would be that I'd take this 47.997, and that would be my part. That would be in the numerator, and I'd divide it by the 100.086. Same question. So that's one way to do these. So let's look at that other type of problem where now we want to know what the formula is, but we're given percentages. And what we're going to do is kind of just really work backwards here, right? So what we're going to do first is we're going to, like I was saying in that earlier slide, we're going to act like we have 100 grams of the stuff. So pretend like you have 100 grams of material, whatever that material is. Because that makes the percentages really easy, right? If I have 100 grams of this material, whatever this acid is, that's 3.09% hydrogen and 31% phosphorus and 65% oxygen. And these are by mass, right? By mass. If I have 100 grams of that, then I know 3.09 grams are hydrogen, that 31.61 grams are phosphorus, and that 65.31 grams are oxygen, right? So if you pretend like you have 100 grams of this stuff, you just start with grams, and then you convert those grams into moles. That's going to be our second step. So first, pretend like you have 100 grams of material, then convert grams to moles. Then convert grams to moles. So let me show you what I'm talking about. And by covert, I mean convert. Convert grams to moles. So I'm going to do the same thing. I'll color code this, right? We've got hydrogen, we've got phosphorus, we've got oxygen. So then what that means is I'm going to say that, okay, let's say we have 3.09 grams of hydrogen. I'm going to convert that into moles. I know that hydrogen is 1.079 grams for every 1 mole. Again, just from the periodic table, just from that atomic mass. So that means then, let's see, so I just go 3 divided by that 1.009, that's going to be about 3 anyway, so 3.07. And then let's go ahead and go to phosphorus here. So phosphorus, so it looks like I have 31.61 grams of phosphorus. Phosphorus weighs 30.9737 grams per 1 mole. And I should have said up here, let me just make sure this is right, moles of hydrogen. So for my moles of phosphorus, it looks like I have 1.02. And then lastly, for my oxygen, we have 65.31 grams of oxygen. And oxygen, again, weighs 15.999 grams of O over 1 mole, or below 1 mole. And that is 4.08. Now, so now I have moles. And now I need to find the ratio between them. And I don't know if you've ever done problems like this. You probably have, but you've probably forgotten. What we're going to do to figure out a nice ratio is we're just going to divide all of the numbers by the lowest number. That's what we're going to do here. So step 2 is just going to be divide all the numbers by the lowest number. By this lowest number. So I'm going to divide, in my case, my lowest number here, right, is 1.02. So I'm going to divide all 3 of these by 1.02. So I'm going to divide this by 0.12, divide this by 0.12, and divide this by 0.12 to get a better looking ratio. I'm trying to get whole number ratios, right, because formulas are in whole numbers. And so if I divide 3.07 divided by 1.02, I end up getting about 3.01 moles of hydrogen. Of course, 1.02 divided by 1.02 is exactly 1 moles of phosphorus. And then lastly, 4.08 divided by that is exactly 4 moles of oxygen. And now I have basically whole numbers. Don't worry if you get a little like straggler number out here, like a percentage or 2. This is basically 3 to 1 to 4. And so that is my mole ratio, or in other words, all of this tells me my formula. I know then that I have, as far as hydrogens go, I have 3 hydrogens. As far as phosphorus go, I have 1. As far as oxygen goes, I have 4. Right? That's where I got these. This 3 is this 3. This 1 from the phosphorus is the one that I didn't write, but it's below the phosphorus. And then this 4 is that 4 right there. So my answer for this would be H3PO4. I think that this acid is phosphoric acid. And that's how you can figure out the formula because you're making mole ratios. So let's do this one too, right? So I want you to do this one, same process. Pretend like you have 100 grams of this stuff. You're going to convert all those percentages into basically grams, convert those grams into moles, and then you're going to compare those mole ratios so you can figure out the nearest whole number ratio by dividing by the lowest one. Right, this one's is saying that L-DOPA is a drug used for Parkinson's disease. It's 54-ish% carbon, 5%-ish of hydrogen, and 7% nitrogen, and 32% oxygen. By mass, what's the formula of L-DOPA? So you're going to follow the exact same process as we did before. So just look at your notes, copy the exact same process, and you should be good. So I'll stop talking for a minute, pause this video, see what you can do. Okay, again, hopefully you actually did that. So we have carbon, we have hydrogen, we have nitrogen, and we have sulfur. Or oxygen, excuse me. So we have 4 now. We had 3 last time, but it's the same exact process. So what we're gonna do is we're just gonna do the exact same thing. So 54.82 grams. Know that carbon was 12. Remember, I'm keeping all of the numbers for the atomic mass. I'm not getting rid of anything in these molar masses. And if you multiply those out, we're going to get 4.564 moles of carbon. Moving along to hydrogen. Hydrogen, it looks like we have 5.62 grams of hydrogen. Sorry, I should have said carbon up here. Hydrogen. Hydrogen weighs 1079 grams per mole. That's going to end up being 5.576 moles of hydrogen. 7.10 grams of nitrogen. Nitrogen weighs 14.007. And that's going to be 0.5069. And then lastly, oxygen, apparently 32.46 grams of oxygen. And again, oxygen weighs 15.999 grams. And that's going to be 2.029. So I've converted all of my masses into moles. Check. The next thing we did, right, was we divided by the smallest one. In this case, my smallest one is the nitrogen one, the 0.5069. So I'm going to divide all of those by the nitrogen one. So 0.5069, 0.5069, 0.5069, 0.5069. So that means now that, sorry, again, I'm just trying to find a better ratio. And if I do that, I end up getting 9.00 moles of carbon. I get 11.01 moles of nitrogen. Sorry, and I should have said carbon up here still. I get exactly 1, right, because I just divided the same 2 things of nitrogen, and I said nitrogen up there. I meant hydrogen. And then lastly, for oxygen, we get 4.002 moles of oxygen. Now, these ratios to me, these look good enough. These are real close to whole numbers. I'm set. If one of these was like, say this was like 9.5 or like 9.3, it was nowhere near a whole number, then I'd have to figure out how I need to multiply all of these up to get them to be whole numbers, right? So if I had like 9.5, and these were all whole numbers, I'd multiply everything up by 2 so I could get whole number ratios. In this case, I don't need to multiply by anything to get whole number ratios. These are basically all whole number ratios right now. This is 9 to 11 to 1 to 4. And so that tells me, again, what my formula is, right? If you put all of this together, it's saying that I have 9 carbons, for every 11 hydrogens. There's only 1 mole of nitrogen in this compound, and there are 4 moles of oxygen. So apparently, L-DOPA has a formula of C9H11NO4. And that's how we do percent compositions. Definitely practice this. It's not crazy hard math. It's just making sure that you have a process that you can follow in order to get to these answers. So study up. Good luck.